10.3 Lesson 1 Parametric Equations and Calculus. Objectives 1. Given a set of parametric equations, you'll be able to find dx dt, dy dt, and dy dx, and understand the significance of each in relation to the curve represented by the set of parametric equations. We'll consider a set of parametric equations that describes the motion of an object in the xy plane, and then we'll interpret each of these derivatives in terms of the object's motion. And then objective 2, you'll be able to find the second derivative for the curve represented by a set of parametric equations. When we look at our theorem that will give us dx, that will give us dy dx, for a given set of parametric equations, we will see why that is true by referring back to something that we learned early on in calculus, the definition of the derivative as a function of x. And then we will also be looking at an example in which we apply the second derivative to analyze concavity at a point. Suppose we have an object in the xy plane, and it is moving, and its motion is described by this set of parametric equations. The x-coordinate of the object at time t is given by t, and the y-coordinate of the object's position at time t is given by t squared. Now, we are saying time can be negative. For example, prior to someone observing, you could have 2 seconds before this particular person starts observing the object. That would be -2 for t. The time at which the person starts looking at the object would be time is equal to 0, and after the initial time of observation, you have positive values for time. So, according to the parametric equation for x, x is just equal to t. So whatever t is, x will be the same. And according to the parametric equation for y, y is equal to t squared. So whatever t is, we will square it. So we have these ordered pairs, and we will plot them: -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And if we connect these points, they will be connected to give us this curve representing the object's motion in the xy plane, and the orientation of the curve will be from left to right. When you look at objective 1, given a set of parametric equations, for example, the set of parametric equations we just looked at, and we're stating that that set of parametric equations will represent the motion of an object in the xy plane. So if we are to find dx dt and dy dt and dy dx, what will these tell us about the object's motion? That's what we mean by understand the significance of each in relation to the curve represented by the set of parametric equations. Today we will learn a theorem that will help us to find dy dx when you have a curve represented by a set of parametric equations. But the other two derivatives that you see before that can be found just by using the differentiation rules that we learned from Calculus AB. So you look at x is equal to t, and if you want to differentiate that equation with respect to t, the derivative of t is 1. So this derivative is just 1. And dy dt, y is equal to t squared. If you want to differentiate that equation with respect to t, you get dy dt is equal to 2t. Before we get to dy dx, let's go ahead and interpret the significance of each of these two derivatives in terms of the object's motion. So you can see that the parametric equation for x, that would tell us the x-coordinate of the object's position at a particular time. In other words, where the object is horizontally. So dx dt would tell us the rate of change of the object's horizontal position with respect to time. In other words, you can use dx dt to determine whether the object is moving to the right or to the left. Remember, if the derivative of a function is positive, that means the function is increasing. So if dx dt is positive 1, that means the object is always moving to the right at a rate of 1 unit of x for each unit of time. If you look at dy dt, we have dy dt is equal to 2t. So if you wanted to know the rate of change of the object's y coordinate or y position with respect to time, it is given by 2t. It is a function of time. So for example, if you wanted to find at the time t is equal to 1, dy dt would at t is equal to 1 would be equal to 2 times t, or 2 times 1, which would be, of course, 2. What that means is at this particular instant in time, at t is equal to 1 second, we know that the object will be here at 1, 1. And dy dt tells us the rate at which the y coordinate of the object's position is changing with respect to time at that instant in time. So it is basically going up because dy dt is positive. If the derivative is positive, the original function is increasing. So the y coordinates are increasing at a rate of 2 units of y for every second in time at that particular instant in time. So that's how we interpret dx dt and dy dt in the context of the object's motion. But what about dy dx? Just like in calculus AB, dy dx represents the slope of the tangent line to the curve at a particular point. So if you want to find, for example, dy dx at time is equal to 1, at time is equal to 1, the object is at the point 1, 1, which is marked here in black, and the slope of the tangent line to the path of the object at that particular instant in time would be, it would actually be 2, and we will see that it's 2 in a little bit. But let me go ahead and first sketch the tangent line to the graph at the point corresponding to the time 1. So what does that tell us? It would tell us the direction of motion of the object at that time. And in fact, the object would be moving in this particular direction shown by the gold marker. So that would be the direction of motion of the object at that particular time. So it's heading in the direction as given by this vector. So that's how we interpret dy dx in terms of the object's motion. Graphically, it would give us the slope of the tangent line to the graph of the function at a particular point. So now the question is, how do we find dy dx if you have a curve represented by a set of parametric equations? Here we have theorem 10.7, the parametric form of the derivative. If a smooth curve C is given by the equations x is a function of t and y is a function of t, of course they could be different functions, that's why we use f and t there, f and g there, then the slope of the curve at xy is given by dy dx. So dy dx gives us the slope of the curve at a particular point, and according to this theorem, dy dx is equal to dy dt over dx dt, provided that dx dt is not equal to 0. So going back to our problem with analyzing the motion of the particle moving in the xy plane, we now know that dy dx is going to be dy dt divided by dx dt. And what is dy dt? We found out earlier that dy dt is going to be 2t, and we found out earlier that dx dt, it's the derivative of t with respect to t, so that's going to be 1. So dy dx, according to the theorem that we just looked at, will be 2t divided by 1. So now if you wanted to find dy dx at a particular point on the curve, such as at the point 1, 1, 1 for x and 1 for y, you have to begin by finding the time at which the object will be at this point. And the time at which the object will be at this point is, for our example, time is equal to 1. So the slope of this tangent line that we had sketched earlier will be given by dy dx evaluated at time is equal to 1. Because at that time, the object will be at the point 1, 1. So what is that equal to? So we will go ahead and evaluate our derivative function at t is equal to 1. So we will have 2t evaluated at 1, which will give us 2, and that is, of course, the slope of the tangent line to the graph of the function at the point 1, 1. So we've already seen a particular example for finding dy dx just now, but let's take a brief look at the proof of this theorem. And when we look at the proof of this theorem, be sure you understand that there are some hypotheses that we are going to rely on to prove this theorem, which is a conditional statement, if then. So what are the hypotheses? We have a smooth curve, and it is given by these equations. And what are we trying to show? That the slope of the curve at a particular point is given by this formula. So how do we do this? We're trying to find dy dx, which is the derivative. So as we go through the proof, you will see that we're going to use the definition of the derivative as a function of x. So if you're trying to show that dy dx is equal to dy dt divided by dx dt, you've got to first understand that dy dx represents the slope of the curve at a particular point. And that's what the theorem is stating, that the slope of the curve at a particular point is given by this formula. So when we think in terms of slope, we may think of the slope of the secant line through 2 points. And then these are the 2 points in this figure. So we have the first point with coordinates f of t, g of t. The x coordinate is given by the parametric equation for x, and the y coordinate is given by the parametric equation for y. So at this first point, the x coordinate is f of t, and the y coordinate is g of t. And at this second point, the object is at point A at time t, and the object is at point B a little bit later. So the time would be t plus delta t. Delta t representing a change in time. And if delta t is really small, then the object will not have moved as much, and point B will be closer to point A. And if delta t is larger, then there's been more time, so the object could be further from point A. So the slope of the secant line through these 2 points is given by the familiar slope formula. How do you find slope of any line? You take the change in y and divide by the change in x. So you would have g of t plus delta t, that gives you the y-coordinate of point B minus the y-coordinate of point A divided by the x-coordinate of point B minus the x-coordinate of point A. So all that tells you is the change in y divided by the change in x, or the slope of the secant line passing through the 2 points A and B. In calculus AB, you will remember that we defined the slope of the tangent line to the graph of a function at a particular point as the limiting value of the slopes of the secant lines as the second point moves closer and closer to the first. In other words, if we want to talk about dy dx in this particular problem, we have to move point B closer to point A, and we have to keep considering the slopes of the secant lines as b moves closer to a, and the slope of the tangent line to the curve at point A would be the limiting value of the slopes of the secant lines as delta x approaches 0. In other words, as point B moves closer to point A. And that's what you see here. So in the figure, consider delta t that's positive, and let delta y, because we're looking for slope, slope is change in y over change in x. So you have delta y here, and then you have delta x here. So you have delta y, and you have delta x. And delta y is what I wrote here. That's delta y. And delta x is what I wrote in the denominator. That's delta x. And again, the idea with the slope of the tangent line is we want to see what happens as the second point moves closer to the first, and we want to find the limiting value of the slopes of the secant lines as the second point moves closer to the first. So when the second point is moving closer to the first, the change in x will approach 0. So we have dy dx, the slope of the tangent line, is given as the limit of the difference quotient delta y over delta x as delta x approaches 0. In other words, as point B moves closer to point A. That's how we define the slope of the tangent line to the graph of a function at a point A in calculus AB. And of course, we replace delta y with what delta y is. It's g of t, change in y, right? G of t plus delta t minus g of t. And we replace delta x with what delta x is. It's the change in x, f of t plus delta t minus f of t. And make the observation that when you have a very small change in time, the object is not going to move that much. So what does it mean that delta x is approaching 0? That will happen when delta t approaches 0. So that's why we have this particular line. As we move forward with the proof, we need to remember the definition of the derivative as a function of x from calculus AB. And it is based on the same concept that we discussed earlier about finding the limiting value of the slopes of secant lines as the second point through which the secant line passes moves closer to the first. And this limit of the difference quotient that you see in the definition gives you what's going on as the second point for the secant line moves closer to the first. And we use the limit of this difference quotient to define the derivative of the function. And because of that, the derivative of the function gives us the slope of the tangent line to the graph of the function at a particular point by definition. So you'll see how he uses that in the remainder of the proof. So because we plan to use this definition, we want to manipulate what we have here, divide both the numerator and denominator by the same quantity. And when you do that, of course, you don't change what you have. You can use the differentiability of f and g to conclude the following. So why do we say the differentiability of f and g? F and g are going to be differentiable because our curve is smooth. So that's how we know that. So now we just manipulate what we have here algebraically, and when we do that, this is what we have. We multiply the numerator by 1 over delta t, and we multiply the denominator by 1 over delta t, and that gives us what we have here. So when you look at this particular line here, we can use the definition of the derivative of a function as a function of x to write the next line. If you look at, for example, the denominator, you have the limit of this difference quotient as delta t approaches 0. that looks exactly like what we have here. The only difference is instead of having x, we have t. So the denominator will be f prime of t by the definition of the derivative as a function. And in the numerator, we have exactly the same thing, but we just have the function g instead of the function f. And of course, the variable is t, so the numerator will be g prime of t. And finally, since the function g tells us what the y-coordinate is, g prime of t is dy dt. And because the function f tells us what the x-coordinate is, f prime of t is dx dt, and that is what you have in this theorem. So what are we learning today? The parametric form of the derivative. When you have a curve given by a set of parametric equations, dy dx will tell you the derivative. It will tell you the slope of the tangent line to the curve C at a particular point corresponding to a t-value, as we saw in our example earlier. And here we have how to find higher order derivatives, such as the second derivative or the third derivative. So what you do is you need to find the first derivative using theorem 10.7, and then after you find the first derivative, you can find the second derivative as follows. So going back to our example, dy dx is equal to dy dt divided by dx dt. So dy dt is 2t and dx dt is 1. So dy dx is 2t. And if you wanted to find the second derivative, here's how you would do it. According to this formula, you need to find the derivative of dy dx with respect to t, and then divide that by dx dt. So the derivative of dy dx with respect to t would be the derivative with respect to t of dy dx, which is given by 2t. Divide that by the derivative with respect to t of x. dx dt is 1. So we have 2 over 1, or just 2. So that's the second derivative that we have for our example that we began with. So we just looked at an example for objective 2. You'll be able to find the second derivative for the curve represented by a set of parametric equations. And now we'd like to look at an example involving concavity, an application of the second derivative. But before we do that, we'd like to do some review of Calculus AB by going back to Calculus AB and reviewing what concavity is. Here's the problem that we want to look at. It is from your textbook. It is example 2, and finding slope in concavity. For the curve given by this set of parametric equations, for t greater than or equal to 0, find the slope and concavity at the point 2, 3. So we will go ahead and do the part about slope, and then we will do a little bit of review of Calculus AB for concavity, and then complete the problem. So to find slope, we will use theorem 10.7, parametric form of the derivative. So to find slope, we need to find dy dx, and theorem 10.7 tells us that dy dx is dy dt divided by dx dt. And then once we find our equation for dy dx, we have to evaluate it at the value of t that corresponds to the ordered pair 2, 3, because we want to find the slope for the curve given by this set of parametric equations at that point. So to find dy dt, you can begin by distributing the 1/4 to t squared and minus 4. That's an optional thing to do. And then for x is equal to square root of t, you'd like to write the square root of t as t to the 1/2. So now we will use the power rule for differentiation to help us find dy dt and dx dt. In the numerator, we will have 1/2 t, and in the denominator, we will have, when we use the power rule, we bring the exponent of 1/2 to the front, and then we will subtract 1 from the exponent of 1/2, giving us a new exponent of t to the negative 1/2. Of course, 1/2 and 1/2 will cancel, leaving us with just t divided by t to the negative 1/2, which is actually t multiplied by t to the positive 1/2. When you move the power from the denominator to the numerator, the exponent becomes positive, and you will have t to the 3/2. You have a product of two powers with the same base, so you add the exponents and you get dy dx is t to the 3/2. You will notice that the problem is asking us to find the slope at the point 2, 3. But when you look at dy dx, which will tell us the slope, it is a function of t. Now, 2 is an x-coordinate, and 3 is a y-coordinate. So 2 is x, 3 is y, but to find the slope at that point, I need to know the value of t that corresponds to 2, 3, because dy dx is in terms of t. So I need to figure out, using my parametric equations, what t should be. And in fact, one of them is enough in this case. So if I replace x with 2, I can solve this equation for t to find that when I square both sides of the equation, I get 2 squared is 4, so t is equal to 4. So when t is equal to 4, I would get the point 2, 3. So if I want to know the slope of the curve at the point 2, 3, I have to evaluate dy dx at t is equal to 4. Of course, you can write t to the 3/2 as t to the 1/2 raised to the third power, power of a power, multiply the exponents there, and you get t to the 3/2. And when we write it that way, we're able to evaluate our derivative evaluated at t is equal to 4. So we have 4 to the 1/2, which is the square root of 4, which is 2, and 2 to the third is 8. So what is the slope of the curve at the point 2, 3? The slope of the curve at the point 2, 3 is 8. We will conclude our lesson by reviewing concavity, and then using those concepts from Calculus AB to complete this problem. To determine the concavity of the curve at the point 2, 3. So let's review concavity here from Calculus AB. How do we define concavity? Definition of concavity. Let f be differentiable on an open interval I. When we talk about concavity, we're always talking about the graph of a function. So we say the graph of a function f is concave upward on an interval I if f prime is increasing on the interval, and concave downward on the interval I if f prime is decreasing on the interval. Now, here is how we interpret concavity graphically. And you can see here the following graphical interpretation of concavity is useful. See Appendix A for a proof of these results. But we can see that these results do make sense by looking at the definition and these two figures. So 1 and 2. 1. Let f be differentiable on an open interval I. If the graph of f is concave upward, the graph looks like the first figure. and the graph of f lies above all of its tangent lines on the interval. So you can see the tangent lines, and they're all below the graph. That's what we mean by the graphical interpretation. But concave upward looks like that. Now, number 2, let f be differentiable on an open interval I if the graph of f is concave downward. If the graph of f is concave downward on the interval, the graph of f lies below all of its tangent lines, on the interval. So you can see that the tangent lines are above the graph. So you should be able to remember the graphical interpretation of what concave up looks like and what concave down looks like. From this definition of concavity, we can also come up with a test for concavity. The graph of f is concave upward on an interval if f prime is increasing on the interval. For f prime to be increasing, the derivative of f prime, which is f double prime, must be positive on the interval I. So if the second derivative of a function is positive on an interval I, then the graph of the function is concave upward on I. And if you look at the definition, the graph of f is concave downward on I if f prime is decreasing on the interval. If f prime is decreasing, the derivative of f prime, or f double prime, must be negative. So if the derivative of f prime, which is f double prime, is negative on an interval I, that means f prime is decreasing on the interval, and therefore the graph of f will be concave downward on the interval. And here we have the test for concavity. Let f be a function whose second derivative exists on an open interval I. If the second derivative is positive on an interval I, the graph of f is concave upward on that interval. If the second derivative is negative on an interval, then the graph of f is concave downward on that interval. Having reviewed concavity from Calculus AB, now we can complete example 2, finding slope and concavity. For the curve given by x is equal to square root of t and y is equal to 1/4 t squared minus 4, for t greater than or equal to 0, find the slope and concavity at the point 2, 3. So we know we can use the second derivative to determine whether the graph of the function is concave upward or concave downward at a particular point. So we will be using the test for concavity. We will find the second derivative and see if the second derivative is either positive or negative, and that would tell us whether if at that point the graph of f will be concave upward or concave downward by the test for concavity. So when you take a look at our work here, we found that dy dx was t to the 3/2. So we're going to go ahead and erase some of the work. So we will have some room to do the work needed to find the second derivative. So we have t to the 3/2 for dy dx. And now we already found dy dx at t is equal to 4, and that was 8, and that gave us the slope of the curve at the point corresponding to t is equal to 4, which is the point with coordinates 2 for x and 3 for y. So to answer the question about whether the curve is concave upward at the point 2, 3 or concave downward at the point 2, 3, we will find the second derivative and see if it's positive or negative at the value of t corresponding to the point 23. So we're using this formula here to find the second derivative. It is the derivative with respect to t of the first derivative divided by dx dt. Now dx dt is 1/2 times t to the negative 1/2. And in the numerator, we have to find the derivative with respect to t of the first derivative. And to do that, we will use the power rule, and we will have bringing the exponent to the front, we have 3/2 t, and then we need to subtract 1 from the exponent of 3/2, and that would give us 1/2. And we have 1/2 times t to the negative 1/2 in the denominator. So now what do? Well, you have 3/2 divided by 1/2, which is the same as being multiplied by the reciprocal. And then you have t to the 1/2 in the numerator, and you have t to the negative 1/2 in the denominator, which you can take to the numerator, and the exponent will become positive 1/2. So when you do the simplification, you get 2 and 2 will cancel here, leaving you with 3 times t to the first power. You have a product of two powers with the same base, so when you add the exponents, you get 1. So you get 3t. That is the second derivative. To answer the question about determining the concavity of the curve at the point 23, remember, at the point 23, x is 2 and y is 3. But when you look at the second derivative, there's no x or y there. It's a function of t. So again, you have to know that this point, you will have this point when t is equal to 4. Because the square root of t gives you x, the square root of 4 is 2. So you have this point when t is equal to 4. So if you want to determine whether the curve is concave upward or concave downward at this point, you will evaluate the second derivative at the corresponding value of t, which is 4. And when you do that, you get 3 times 4 is 12, and that is a positive number. And if the second derivative is positive, the graph is concave upward. So we know when we evaluate the second derivative at t is equal to 4, we get 12, and therefore, it being positive, the graph must be concave upward at the point corresponding to t is equal to 4, which is the point 23. And here I write the conclusion that we are concluding that the curve is concave upward at 2,3 by the test for concavity, and we're able to do that because we have found the second derivative to be positive at the value of t corresponding to the point 23. This is the graph for example 2. Here's the curve represented by the set of parametric equations. We have the point 23. As we found in part 1 of the problem, the slope of the curve at that point is 8, and you can see from the graph here that at this point the graph is in fact concave upward. So today we looked at interpretation of dx dt, dy dt, and dy dx in terms of motion in a plane, and we also looked at how to find the second derivative and the first derivative for a set of parametric equations, for a curve given by a set of parametric equations. And we also reviewed some calculus AB.